In this video, I'm going to give you some visualization tools for the concepts of linear combination, linear independence, and span. So the reason why I chose these three words is because they are very crucial in linear algebra and they come up all the time. Like almost every theorem uses at least two of those three words. And so you need to have something visual, you need to have some intuition, something that pops up that's meaningful when those words come up. Otherwise, your lectures are just going to sound like a big jumble of words where every other word is linear combination, span, or independent. So it's going to sound something like this if you don't have any visualization, blah, blah, span, blah, blah, linear combination, blah, blah, independence. And so you really want to have something pop up when those words come, and this video will show you some visualizations. So I'm going to start with an analogy, and I'm going to think of my vectors like building blocks, sort of like Tinker Toys or other building blocks that you might have played with. Things that had Tinker Toys is especially appropriate because they are like these sticks, and they have short sticks, they have longer sticks, so they're different sizes, and then you can point them in different directions, and then you add them together to make structures. But I'm just going to use the term building blocks to indicate it's some other smaller piece that you're going to build bigger structures from. So you can think of your vectors as building blocks that you can use to build bigger structures or other blocks, bigger blocks, or other vectors. So if you have a particularly really good set of vectors, it'll allow you to build everything you can think of, and that's considered your space. And a very elegant set of vectors or blocks allow you to build everything with a minimum number of vectors. So these vectors are considered very powerful because it's not a lot of vectors, not a big tool set that you need, but like from this small little tool set, you can basically, it's complete. It's small but complete. It can build everything, and it's very efficient. That small little elegant set is the idea of a basis. So the first thing you have, or tool that you have to work with your building blocks, is multiplication by scalars. And that allows you to adjust the length of your building blocks. So if you multiply by something between -1 and 1, you're going to be shortening your building block. And then anything where the absolute value is greater than 1, you're going to lengthen your building blocks. Or you can think of the Tinker Toys, you're going to lengthen those sticks. The next tool you have are linear combinations, and basically linear combinations are basically how you build new vectors. That's kind of like when you start combining things. So after you scale your building blocks, then you add them together. You just do the addition. So your linear combination is basically the two things, the scaling and then adding them together. So then we have the idea of linear dependence. So if you have a vector that's dependent on other vectors, that means that vector can be built from other vectors, basically through linear combination. We should contrast that with linearly independent. So if a set of vectors is independent, you cannot build one from the others. So they're basically independent pieces. And in this way, each piece is special because it cannot be made from the others, and there's something unique about it that you might like or that you might need. So linearly independent, again, it's something, each one is kind of unique, cannot be made from others. And then the last concept in this building analogy we want is span. And the span is basically describes what you can build with your set of vectors. It's what you can achieve. And it's no accident, I think, that it's called span, because if you think of a wingspan of a bird, you're talking about how far it can reach. And that's the same thing as with these building blocks. What is it that you're able to achieve? What can you reach? What can you touch? And then also, what is out of your reach? So that's the building block analogy, so I hope that helps you. So now I'm going to give you some visual tools using R2, just to give you a more concrete example and visual example. So going back and also just talking about these building blocks, remember the vectors stand for something, probably something, maybe something in the real world, maybe they're colors, maybe they're audio sounds, maybe they're game moves or financial markets. But anyway, they stand for something. So let's just think about colors. So if you have a set of building blocks, the span of your colors those are like let's say you have 12 colors and that's your vectors. The span of your colors then is all the colors you can make from that. So if you have a set that you can build any color that you want, that means your set of paints is a really good set of paints, and it spans the space of colors that you want to paint. And then the elegant set of vectors, by the way, that's called a basis. That's when you have, I think in watercolor, is it like blue, red, and yellow? Theoretically, you can mix it and make all the other colors. So that would be a basis, a very minimal set of colors that's really powerful because it lets you make all the other colors. You know, if I got my color theory wrong, I'm sorry, I don't really do art, but that's the idea. So for my vector example for visualization, so I'm going to start with two vectors. The first one is 4, 2, and the next one is 1, 3. And my question is, what is in the span of 4, 2? In other words, remember the span is all linear combinations of 4, 2, and 1, 3. In other words, what vectors in R2 can I make using 4, 2, and 1, 3? And again, the tools I'm using to make new vectors are linear combinations. And the easiest, quickest thing I can do is just add a plus b directly. So to add a plus b, I move the vector a up to here, and then the endpoint is my endpoint for a plus b. And then I have it algebraically done here. So here's my a plus b. The next thing I could think about is I can scale a. So here's twice a, and I took twice a, and I moved it up to the head of b. So here's my vector 2a plus b. Here it is algebraically, which well, my graph is pretty decent, so I have hit the correct point. Other ways I can scale this, maybe I'm just going to take half of a, this half vector, move it up, and I get 1/2 a plus b. Here it is algebraically. And then last, just to be a little bit complete, I can take negative a. So here's a, I have negative a, which points in the opposite direction, or negative 4, 2. I move this vector up to the head of b, and I get negative a plus b, and here it is calculated algebraically. So those are just some of the linear combinations when I change the coefficient in front of a. So just taking another look at my graph so far, if I had a plus b, I get this point, 1/2 a plus b, I have this point, 1/4 a plus b, I'd get this point on the line. Here is my 2a plus b. And then when I go negative, I start getting these points on the line. And just to remind you from vector calc, if you wanted to parameterize an equation of a line that goes through point B and the direction of vector A, you would parameterize it as A times a variable t plus your point B. And I'm sure you remember this from vector calc, and you can do something similar for a line going through B in the direction of A. But this method of scaling A and then adding to B is how you get all the points along this line. And then you can do something similar for scaling B and adding to A. So we know how to get things along this line here, and we know how to get things along the line going through A in the direction of B here. So what about all these things inside? So basically you're just going to be scaling A less than 1 and B less than 1, and when you add them, you're going to get all these points inside this parallelogram. Again, any scaling of A less than 1, any scaling of B, then add them, and you'll get all of these points. All of these vectors are reachable just by scaling between 0 and 1. But really the question becomes then, what about all these other points outside? So essentially, I'm going to show you if I extend A and I extend B. And again, what we can see is that along here, as long as we're scaling between 0 and we stay positive, in other words, t, if we're scaling A by t, t is our scalar, as long as it's positive, and here, as long as B is positive, we're going to reach all of these points here. Down here, we want A to be positive, but we're going to scale B negative. So once we have a positive A and we add it to a negative B, we're going to get a point in this range here. And that's what this is. A is positive, B is negative. B, S is what we're scaling B by. Over here, we have, in this area, we have A is going to be negative, so our scale has to be less than 0, but our B is positive. And then here's where A and B are both, oops, this should be less than 0, not less than infinity. So can I scratch that out? So I'm going to scratch this out and put T and S are less than 0. Okay. So what I've shown here is that these two vectors, and I just drew A and B, I chose them kind of randomly. Any two vectors in R2 will span the space. Actually, I need to correct that. Just there's one exception, and almost inevitably this one exception is going to appear on an exam for you somewhere. But essentially, any two vectors will span R2 unless the two vectors are multiples of each other. In other words, something like 1, 2, and 2, 4. You know, because basically 1, 2 is this vector, and then 2, 4 is kind of giving you the same information as far as building blocks go. It isn't helpful because it's just a scalar multiple of another, basically because you can get 2, 4 from 1, 2. And there's, I think, later in chapter 2, we'll do a formal proof that if one is a scalar multiple, they can't be linearly independent. And, you know, from the things I was talking to you about building blocks, they can't be linearly independent because obviously you can make this one from 2, 4 from 1, 2 just by stretching this one out. So again, any two vectors that are not scalable multiples of each other will span your space R2. So that's it for this video. I just wanted to give you an analogy and some visual tools to get you comfortable with these ideas because they are so central to understanding the rest of linear algebra. Thank you for watching. Bye-bye.